Hey guys, in this video, we'll be going over gradient descent in practice. Specifically, we'll be diving into something called feature scaling. So in the previous videos, we discussed a little bit about features, which are ways to categorize our input. And in the context of predicting the price of homes, some features may include, the size of a home, the number of bathrooms. And we would denote this in our model here as x1 and x2. Okay, so the size of a home, x1 in this case, maybe like 500 square feet, okay? And the number of bathrooms, which we'll denote as x2, maybe something like 3. So you can see that x1 and x2 vary drastically in value, right? 503, very different in numbers. And when we multiply that by a value w1 and w2, say, for example, actually, that w1 and w2 are equivalent, okay? So we're multiplying x1 by, say, 2, and we're also multiplying x2 by 2. In our model, x1 will actually have more weight. Because think about it, 500 times 2 is 1,000, 3 times 2 is 6. So x1 is having more of an influence on our output. But we don't necessarily want that all the time. The size of a home and the number of bathrooms could equally contribute to the price of a home. So we have a dilemma here. So to ensure that the two features contribute equally to our output, we'll have to adjust W, our parameters, accordingly. So I can represent the effects of both parameters, W1 and W2, on the cost function by using a contour plot, which is something we haven't discussed yet. It looks something like this. Okay, so notice in this case, the axes represent the parameters W1 and W2. However, we said that some features will have more of an influence on our final model, and we said that we would have to compensate for that by changing our values of W2. So you can see that W2 here is much larger than W1 to compensate for the smaller value in one of the features. Okay, but what that does is it skews our contour plot. So this is a contour plot. However, because the scales aren't equivalent, our contour plot is actually very skinny compared to what a regular contour plot would look like, where it's more circular. And this occurs when W1 and W2 are represented on more of an equivalent scale. And a contour plot, what it is a way of representing how our cost function reaches its minimum. However, when our contour plot is extremely skinny, which happens when we have to compensate for a feature by making one parameter or a W value much larger than the other, is that our cost function actually has difficulty reaching its minimum. So it might start from a point like this, and it'll actually zigzag here until it reaches a minimum. And sometimes it doesn't even reach the minimum. Whereas if our parameters were on an even scale, it would be very straightforward to reach the minimum. So to summarize, the problem was that one feature had more of an influence on our output, and we tried compensating for that by changing the scale of our parameters. However, this yielded not a more circular contour plot, which thus makes it less likely that the cost function will reach its minimum. So given that our features are on different scales, how can we still make the contour plot look something like this, where the parameters are on an even scale and thus the cost function has an easier time reaching its minimum? Well, we can do this by doing something called feature scaling. Okay, so say one of our features, x1, varies from 300 to 2,000. So this might be the size of the homes. Okay, so x1 in this case will represent the size of homes, and we'll say that it ranges from 300 to 2,000, meaning we can have, a very large data set, and the minimum size will be 300 square feet and the maximum size will be 2,000 square feet. And we'll say other feature x2 will represent the number of bathrooms, and this will range from 0 to 5. Okay, well, for our w's, for our parameters to be on an equivalent scale, we want our features to be on an equivalent scale. So what we do is we scale down our features so that both of our features, right, the number of bathrooms and the size of our homes, are on a more similar scale. So we are going to scale x1 here, the size of the homes. Okay, so to execute feature scaling, what we're going to do is we're going to loop over each specific feature, so in this case the size of the homes, and divide it by the maximum number in this feature. So in this case it's 2,000. That's the largest that's the largest size of a home in this training data. Okay, so now x1 will range from 0.15 to 1, because remember, we're dividing each value by the maximum value. So 300 divided by 2,000 will be 0.15, and 2,000 divided by 2,000 will obviously be 1. So now x1, which represents the size of the homes, which is a feature, is now going to range from 0.15 to 1. And we're going to do the same thing with our other feature, the number of bathrooms. So we're going to take each feature and divide it by the maximum value, which in this case is 5. Okay? It's 5 in this case. So now these features will range from 0. So before, if we were to plot our data, let's say the x-axis represents x1 and the y-axis will represent x2, and it ranged like this, and we kept it at its original scale, the data would look something like this. And this corresponds to a skinny contour plot. However, by feature scaling it, now if we plot our features side by side, the scales are more equivalent. So x1 will still be represented on the x-axis and x2 will be represented on the y-axis. And the scales of our x-axis and y-axis, however, are going to be on a similar scale, because now you can see that, hey, x1 and x2 both range from 0 to 1 now. So now our data is going to be something like this. And this corresponds to a more circular contour plot, which thus means our cost function will have an easier time reaching its minimum. There are other ways we can also rescale our data. So we just talked about feature scaling. There's also something called mean normalization. And so in mean normalization, instead of our feature values ranging from 0 to 1, it'll range from -1 to 1 for both features. So now our data, when plotted, will look something like that. Okay, and the way we do this is by using mean normalization. So we'll use the same features as we did when using feature scaling. So our first parameter will be x1. And we said that x1 ranges from 300 to 2,000. Okay, and to execute mean normalization, what we do is we change each feature with this formula. So we take it and subtract it by mu1. And what mu1 represents is the average of these features. So all these features, all the data from this specific feature, so all of the price of the homes in this data set, we are going to take that and average that. So we'll add them all up together and divide it by the amount of data points we have. And that will represent mu1. So the average of the price of homes. And what we're going to do is we're going to divide this by the difference between our max and minimum. Okay, and our max and minimum in this case, max is 2,000, right? This is our max. And our minimum is 300. This is our minimum. So when we execute this, we'll get that our x1 value ranges from -0.18 to 0.82. And we'll do the same thing for x2 again. So x2 originally has a different scale, right? Instead of ranging from 200 to 3,000, x2 only ranges from 0 to 5. And we'll apply mean normalization. So now each x2 feature is going to be changed by subtracting mu2. So mu2 in this case, which is the average of this specific feature, subtracted by the maximum minus the minimum. So that's just 5 in this case. And what that will get us is now x2 ranges from -0.46 to 0.54. Okay? And you can see that, hey, both features, instead of having completely different scales, look, now they range from -1 to 1. Do you see that here? So when plotted, it would look something like this. And this also corresponds to more of a circular contour plot. Okay, the last form of rescaling our features is called z-score normalization. Okay, so applying z-score normalization, what we're going to do is, in the numerator, it's going to be a similar process to mean normalization, where we take each feature and we're going to subtract from it the average. So in this case, mu1. Okay, but instead of dividing by the difference between the max and minimum, we're going to be dividing by something called the standard deviation, which is denoted as this symbol right here. So this symbol represents the standard deviation for this specific feature. And we don't need to go into depth of standard deviation here, but just know that it is a number, okay? And we're going to be dividing this business over here by the standard deviation. And when we apply this, we'll get that our features will now range from negative 0.67 to 3.1. Similarly, we'll apply the same process to x2. So x2 is going to be equal to x2 minus mu2. Remember, mu2 is not equal to mu1 because mu2 is the average of this specific feature while mu1 is the average of another feature divided by the standard deviation. Subset 2. So this feature also has its own standard deviation. So know that the standard deviation, these two aren't equivalent either. Okay? And x2 now will range from negative 1.6 to 1.9. So when we plot our data points now side by side, we'll see now that it ranges in this scale. Okay? So to summarize, using feature scaling, mean normalization, and z-score normalization, we are able to convert our contour plot from looking something like this, where it's very skinny, to something more circular, which helps our cost function reach its global minimum. Okay, and instead of having skew data plots where it extends in the horizontal or vertical place like this, now our data will range in parameters that have a more equivalent scale, as we've shown here. Okay, but before I send you off on your way, we need to go over what the goals of feature scaling are. Okay, so using feature scaling, we want our features ideally to range from -1 to 1. And we've done that. We've done that here for the most part. It's also important to note that it doesn't exactly have to range from -1 to 1. These are our loose constraints. So it can range from, -3 to 3. However, we don't want to see x's range from something like this, where it ranges from -100, let's say, to 100. This is too large. Nor do we want to see something too small, where it's like -0.001 to 0.001. And even if the difference between the two constraints are small, so if we had something like 98.6 to 105, this is still too large. So these two are too large, and this one's too small. For both, they're not good. So we'll have to rescale it in order to get it into this form. Remember, it doesn't have to perfectly be in that form, but that's our ideal goal. Okay, I hope you enjoyed this video. Thank you for watching.